All right, so let's go back. Let D be the greatest common divisor of I and N. Because now that we have this limit, now we're going to start bringing in some of this greatest common divisor stuff from before. Okay, so let D be the greatest common divisor of I and N. Okay. So by the way, let K be all integer multiples of K mod N. So so this would probably be better written K times M mod N Z. So this is NZ mod NZ. Okay. So basically what this is we're just taking like all multiples of K mod Z. Okay. Then I claim that I equals D. We have this direction is straightforward because D by definition is the greatest common divisor of I and N, so D divides N. No, D divides I. Well, it does divide N, but what we care about here is that D divides I, so I is MD for some integer M. I mean, it's going to be a positive integer, but we'll say integer. So if we have any element J in I, then J is equivalent to I yeah, so this is basically this is just like some multiple of I. So there is some M O P, so J is equivalent to B I mod N for some integer P. So remember I equals MD, so J is equivalent to D times MP mod N, which means precisely that J, so J is a multiple of D as well. Mod N, which means that J is in the this is called the subgroup of Z mod NZ generated by D. I didn't go into the group theory stuff here because I didn't want to get that deep. I suppose some group theory background is useful or possibly necessary, certainly useful for this proof. So if you don't have it, sorry. I guess go watch my group theory videos and like them and subscribe and comment, all that stuff. But yeah, learn group theory. Anyways, yeah, so we have J is in here. And that holds true of any J and I. And thus, I is a subset of D. Okay, so for the other direction, by Bezos, by this lemma or identity, whatever it is, we know that we can write, so here there exists integers x and y such that D is equal to xi plus yn, because D is the greatest common divisor of I and n. And so this is exactly what the lemma tells us. So if we take this mod n, then the yn is going to drop out. So D is equivalent to xi mod n. So now what this tells us is, so D is actually a multiple of I mod n. And then that gives us, and then we get to do the same argument in reverse. So if J is in D, then J is equivalent to PD mod n for some P. So J is equivalent to, what's here, PD. So then we have X times I times D mod n, and because this is a multiple of D, this means precisely that J is in the subgroup generated by D. And because this holds for any element J of D, wait, no, I went back, no, it's I. Well, obviously it started in D, it's obviously in the subgroup generated by D, but it's in the subgroup generated by I because it is a multiple of I, an integer multiple of I mod n. So J is in the subgroup generated by I, and this held for any element J in the subgroup generated by D. And so thus, D is subgroup generated by D is a subset of the subgroup generated by I. So hence, I equals D. Okay. All right. So, and what does that tell us? Just going back a little bit. So when we talked, I've written a lot. So talking back about this example, here we had I equals 4. And so we were talking about like A, we could start with A and then we move up by 4 and we'll get something that's equal 1, 2, 3, 4. Then move up by 4, get something that's equal, move up by 4 again. And so basically we got, what we're looking at here is the subgroup of n mod 6, n generated by 4 is going to be 0, 2, and 4. And so these things are equal. And basically what we talked about was that like if we're incrementing by 4, then the indices that generates is the same as incrementing by 2. And so another way of saying that is like if you're looking at the collection of underlying indices, for one of them you have the subgroup set generated by 4, and for one you have the subgroup generated by 2, and we see that they're exactly the same. And so that's what this is saying, is that the subgroup of indices generated by the offset index is equal to the subset of indices generated by the greatest common divisor of that offset with the length of the original string. Okay, so now what do we have? Since since D divides N, what do we have? What does this set look like? Well, when we looked at here, like it's kind of straightforward. Like, what does the set of indices generated by 2 looks like? Well, you start at 0, then you get to 2, and then you just include all multiples of 2, which are strictly less than n. And so how many of those did we have? We had no, this isn't right. Okay. D is equal to 0, D, then we're going to go all the way up to n minus D, right? Right, because the fact that D divides n means that there is some multiple of D that is equal to n. And so whatever that, once you get to that index, you wrap around to the beginning and you start back at 0. So all the indices that you hit before then are distinct. So the elements of the subgroup generated by D in Z mod NZ is precisely 0, D, all the way up to n minus D. And we have how many elements here? Yeah, we have some number of elements. It doesn't really matter. The point is D is equal to this because of the fact that D divides n. Okay. So now what do we have? Let D plus J be equal to all numbers of the form dm plus j mod n, where m is an integer. So these are going to be in Z mod NZ. Okay. Then these sets D, D plus 1, all the way up to D plus, and we're going to go all the way up to D minus 1, are disjoint and cover Z mod NZ. They cover all the integers. Well, here, let's write it this. They cover all the integers from 0 all the way up to n minus 1. Yes. Okay, and why is this true? This is true because basically you take any, so they're disjoint because basically any element here is going to be dm plus j mod n. And so if you take the remainder, yeah, basically, so if you take the remainder of any element in here after dividing by d, you're going to get remainder 0 because it is an integer multiple of d, because it's in here. Now, if you look at this, yeah, by the way, this is mod n. Excuse me. Okay. Yeah. So now if you add 1, then if you take the remainder of any integer in here, take the remainder after dividing by d, then the remainder is going to be 1, because it's just some integer multiple of d plus 1. I mean mod n, of course, but that doesn't really matter because d is basically, it's just integer multiples of d. Even n minus d, right? Because this is 0d, 2d, 3d, 4d, 5d, all the way up to n minus d, which will be a multiple of d. Okay. So, and basically, just really quick here, so d divides n means that there is some integer m such that d times m equals n, and so then this final index here will be m minus 1 times d. Because if you were to go further, you would get to md, which is equal to n, and mod n, that gives you 0. Okay, so these sets are disjoint because if you take any two of them, the remainder after dividing by d is going to be equal to whatever this additional translation is here. So so these are all disjoint, and they cover all the integers from 0 to n minus 1. And the way that you know that is you just take the integer and you take the remainder after dividing by d, and whatever that remainder is will tell you which of these it belongs to. So if the remainder is 1, then it belongs to d plus 1, because by definition, the fact that you divided by d and got remainder 1 means that it was a number of the form md plus 1 for some integer m. Okay, so these are disjoint and they cover this thing. Okay, so okay. Sorry, at the end here, this is sort of just like a bunch of random facts coming together here. I suppose I could have made this neater. Recall Sj equals S j plus mi mod n. This implies that Sj equals Sx for any x in G, no, sorry, different notation. For any x where x is in D plus, I'm going to write this as n% I. So this is the remainder that you get when you divide n by I. Ooh, no, is that I? Should it be D? Yeah, it should be D. Right, because D is yeah. So right, and this is okay. Instead of writing this out, I'm just going to explain this. So this collection J plus Mi, these are going to be like multiple. This is basically taking J. Okay, because J plus Mi mod n, this is going to be the subgroup generated by I plus J which is equal to the subgroup generated by D. Well, I don't even need this parentheses. This is just the proof. This set is equal to the subgroup generated by I plus J just by definition, because subgroup generated by I is just anything of the form mi mod n, and then you just add J to it. Okay, so it's just this. And it's, of course, like this, like mod m, but whatever. Okay. Yeah, it's everything here is mod n. Okay, so this plus J. And then we know I equals D, and so this equals this plus J. But then because we know that 0 through n minus 1 only consists of these distinct subsets, basically we can take any, if J is, we can divide J by D and get the remainder, and anything that's not in the remainder just gets sort of like consumed into D. Subsumed? I don't know. Definitely not consumed, but that's a cool word. So this is equal to D plus n percent J. No, this isn't quite right. The remainder f would take J divided by D, so I don't know why I had n here. Okay, cool. So, and basically this gives us what we want. And so, thus S is n divided by D copies of S from 0 to D. Right? Because the indices from 0 to D are going to each belong in one of these distinct sets. And so there's not going to be any sort of like relations that you don't get any automatic relations between characters there. But then once you get to index D, because remember this is indices from 0 to D minus 1. Once you get to index D, then that's going to belong to this set. And so S of D is going to be equal to S of 0, and then S of D plus 1 is going to be S of 1, blah, blah, blah. So you're basically just going to loop back around here. And because these like loop continuously and they cover the entire thing, this is going to cover the entire string S. So S is equal to n divided by D, which we know is going to be an integer because D divides n, multiples of this. Okay, so I don't know. It's kind of funny. So remember, return S in S. So remember this. This was the only code that we needed in order to solve the problem. But in order to prove that this actually works, we had to do all of this work. So, I don't know. I think that's pretty incredible that we were able to do this. But yeah, so this is so obviously, like if you're solving this problem on your own, like this is not an easy thing to come up with, like to actually like write out the proof. You could probably like sort of see the pattern in your head and think like, oh, this probably makes sense, modular arithmetic, blah, 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 something like that. But yeah, to actually like prove this, you have to do a lot of work, and then you get to do a very simple thing at the end. And I don't know, I think it's just really neat the way that math allows you to consolidate complex topics succinctly. Like we have this small statement here, which, okay, well, I guess this doesn't like contain the information of the proof, but it relies on the proof, and the proof, it's like such a small, it's such a simple statement that has such a significant proof. And I just think that's neat.